Hello, everyone, and welcome back to Math Zone African Motives. So, today I want us to look into grade 11 physical sciences, where we are going to be looking into a topic that is called Newton's laws of motion. So, just a recap, we've done a video where we were looking into grade 11 physical sciences for term 1, where we looked into vectors in 2 dimension. That is the introductory topic where you get introduced to grade 11 stuff, where you do a recap on what you have done in grade 10. So this topic, Newton's laws of motion, it's a continuation from vectors in 2 dimension. So now what we are going to be looking into, the lesson objectives of this lesson is we need to understand the Newton's laws. So we know that they are what we refer to as Newton's laws of motion, which is Newton's first law, Newton's second law, and Newton's third law. We need to understand, be able to state and define those laws, and we are going to investigate the relationship between force and acceleration. This is usually in relation to Newton's second law. And then we are also going to interpret experimental data, which we are going to get from the investigation that we are going to be looking into. And then thereafter, we are now going to look deep and apply Newton's second law to real life situations. And then thereafter, we are going to dive deep into practice questions where now we are now applying Newton's laws in terms of determining different types of forces as well as working out problems. So without wasting time, I would want us to start by going through the Newton's laws of motions. So you would find out that the first law that was determined by Sir Newton is known as the law of inertia, where we know that inertia is a property of an object or else of a substance that determines the resistance to change in motion. What makes us resist to change any type of motion? Like, for example, if I'm seated, if someone wants to push me, I've got that tendency to resist that move of push. Or else, let's say that I'm in a car and then I get to apply a sudden application of brakes, and then you would get to see that I would continuously move uh, towards the steering. If I'm not wearing a seat belt, I would actually get to what? I would actually get to hit my head on the steering. So what causes that is what we refer to as inertia. This is the property of a body to resist any type of motion. If you are seated at the back of a bakkie and then the driver just suddenly applies some brakes, you see yourself moving forward or else continuously moving forward with the same speed up until you find somewhere to hold on to. That is what we refer to as the property of inertia. So what is it that the first law says? Newton's first law says that an object remains at rest or moves at constant velocity unless acted upon by a net external force. So that is what we refer to as the law of inertia. And then we have what we refer to as the second law, which is the Newton's second law. Newton's second law states that if a net resultant force acts upon an object, or else if a net external force acts on an object, the object will start to accelerate. And the acceleration of that object would be in the same direction as the resultant net force. And you get to see that the acceleration produced is directly proportional to the resultant force and inversely proportional to the mass of the object. That is what Newton's second law says. So In some other cases, we usually define Newton's second law, using a formulation which says F net is equal to mass times acceleration, where we are saying the acceleration is in the same direction as the net force applied. So what it simply says, or else what this formula defines, it simply says that whenever we apply a net force to an object, the object will start to accelerate, and the acceleration would be in the same direction as the net force, and it would have the magnitude that is directly proportional to the what, to the magnitude of the net force applied. But however, you would get to see that even though our net force is directly proportional to the what, our net acceleration is directly proportional to the net force, you would see that the acceleration would be inversely proportional to the mass of the object, meaning to say that the greater the mass of the object, the smaller the acceleration, and then the smaller the mass of the object, the greater the object will accelerate. That is what Newton's second law simply states. Now that we now know Newton's first law and Newton's second law, we now need to define and state Newton's third law. You would see that Newton's third law, it is simply a law that gives us the law that actually defines the interaction of two bodies, or else the interaction of two objects. So you would see that this law simply defines that objects interact in pairs, or else forces they interact in pairs, where it says that whenever we have got object A and object A interacts with object B, you would see that object A exerts a force which is force A on object B that is equal to the force that object B will exert on object A, but opposite in direction to the force that is exerted by what? By object B. So in actual essence, the definition that we might take, it states that when pairs of objects interact, they exert forces on each other. When pairs of objects interact, we have got object A and object B. You would see that these two objects, they exert forces on each other. If object A exerts a force on object B, object B will exert an equal force on object A, but in the opposite direction. That is what Newton's third law simply states. So now that we now know the three laws, or else the three Newton's laws of motion, let's now dive deep into Newton's second law. This is the most important law that we are going to be applying and using in grade 11 syllabus. And also this law, you will see that it is also muchly examinable as well in grade 12. So now we now want to actually get to dive deep into investigating this law, because most of our questions will hinge on this law, or else most of our application questions will come out of this law. So most of our marks that would be examined on will be coming on Newton's second law. So as we have said, that Newton's second law is determined by a formulation that says F net is equal to m times a, where it says mass times acceleration. So we are simply saying that acceleration is directly proportional to the what? To the net force. The acceleration that the object would have after applying a net force is directly proportional to the applied net force. But however, you would see that even though we have said that our acceleration is directly proportional to net force, the acceleration is also inversely proportional to the what? To the mass of the object. So I've got two diagrams here which are graphs which are defining Newton's law, where we have got the first graph which is given as our acceleration against our what? Our applied force, where you would see that the force is directly proportional to the what? To the acceleration, or else the acceleration is directly proportional to the what? To the net force applied. So using graphs, you would see that we will always draw our net force on the x-axis, while our acceleration will always be on the what? On the y-axis, where we will define our net force as the independent variable, where the acceleration would be the dependent variable. So that as we change our net force, you would see that as you increase your net force, the acceleration will also get what? To increase. That is what this graph simply means. And that is how we would be applying this graph in the next coming application what? Application questions. Now, we also have got another graph that would be of acceleration against the mass of the object. So you would see that the mass of the object would be the independent variable, whilst the acceleration would be the dependent variable, in such a way that when we are to increase the mass of the what? Of the object, when we get to increase the mass of the object, you would see that the acceleration of the object would then get to decrease. So we then get to say that the acceleration of the object is inversely proportional to the mass of the object. So our diagram, or else our graphs that we'll be drawing, where we need to investigate the relationship between mass and acceleration, would be given by a graph that is in this format. So I would need you to remember these two graphs very well, and remember how we tend to apply them in real lives, or else how we tend to apply them in the practice questions to come. So now let's go on to look into what we refer to as what? As force. What is it that we define as force? You would see that force is any interaction that can change the motion or shape of an object, or even the direction of an object. So any interaction between two objects that can change the motion or shape of an object is what we refer to as the what? As the force. So this is the definition that we are going to be adopting, where we are saying that a force is any interaction. A force is any interaction that can change the motion, the shape, or else the direction of an object. And this is measured in units. These are the SI units of force. They are measured. You know that force would be measured in what? In newtons. And our force is a vector quantity, and we know that vector quantities, they possess both magnitude and direction. So our force is a vector quantity that possess both magnitude and direction. So to fully describe force, you need to mention its magnitude as well as direction. That's why we are saying that our acceleration of the body will be in the same direction as the net force. And then the magnitude, which is the size of the acceleration, will be directly proportional to the size of the net force. Meaning to say that both acceleration and net force, they are vector quantities. Hence, therefore, you need to determine both their magnitude and direction. Also, we need to define what is it that we state or we mean by acceleration. So we know that acceleration is the rate of change of velocity, where we are saying acceleration can be given by the what? Rate of change of velocity, which is change in velocity divided by the change in time. And our SI unit of acceleration is meters per square second. meters per square second. An object might be said to be accelerating only if its speed changes. Wherever we have got a change in velocity or a change in speed, we know that we have got what? Acceleration. It might either increase or it might decrease. When it increases, we know that our object is what? Is accelerating in the positive direction. Whenever the object decreases in speed, we know that our object is what? Is decelerating, meaning to say that it is accelerating in the negative direction. So it simply means that whenever also we have got a change in direction of an object, or even though its speed is constant, but whenever there is a change in direction, it simply means there is also what? An acceleration of an object. It simply means that also our object is what? Is accelerating. So that is how we define force, and that is how we define acceleration. So that in the next coming application questions, we now know what force and acceleration simply means. After we have said that, now we want to dive into the Newton's second law, but we now want to use an investigation. We have got an experiment that we use to investigate Newton's second law. This experiment, it helps us to determine the relationship between force as well as acceleration while we are keeping our mass constant. So we want to look into an investigation that you are going to do in your classes at your schools. So within a physical setup, you are going to do this investigation physically, where you are going to use a trolley as well as a pulley and different masses to investigate the relationship between force and acceleration. So within that experiment setup, you would now be asked, what is the aim of this experiment? So the overall aim of the experiment would be to determine the relationship between what? The net force and the acceleration, while keeping the mass constant. And this is where your investigative question would come from. So at some point in time, they would say that determine an investigative question that you can come up with from this experiment. That investigative question would be to say, what is the relationship between the net force and the acceleration while our mass is constant, or else while we keep our mass constant? So you would see that within this experiment, you are going to have different variables, where you are going to have what we refer to as the independent variable, where we say that this independent variable, it does not depend on any other variables, but other variables depend on it. Like for example, on this experiment, our independent variable would either be net force, or else it can also be mass. But here we said we want our net force to be our what? Our independent variable, because we want to determine the relationship between our net force and acceleration. Therefore, the independent variable for this experiment would be our net force. So that our acceleration will now depend on how we vary our net force. If we increase our net force, what happens to our acceleration? If we decrease our net force, what happens to our acceleration? That is what we want to determine. Hence, therefore, our independent variable is going to be the what? Is going to be the net force. But our dependent variable is going to be the acceleration. After we have determined our independent variable and dependent variable, this is what we have determined by those graphs that I was showing you, so that our acceleration would be on the what? On the dependent variable axis, which is our y-axis, and then our net force would be on the independent variable x-axis. So when we are now drawing our graphs, you would see that our acceleration would be in the y-axis, whilst our net force would be in the x-axis, because we are saying our net force is the independent variable, whilst our acceleration becomes the dependent variable. And then within that experiment, you would see that we are going to have what we call controlled variables. The variables that we are going to maintain constant, the variables that we are only going to change after we have determined our results between our independent and dependent variable. And this controlled variable within this experimental setup is going to be our mass, our friction, and our track angle, where we are saying that we are going to keep our mass constant. We are only going to use the same mass throughout the experiment. And then we are going to use the same surface so that we keep our friction constant. The same surface will have the same frictional constant, or else it will have the same what constant of what frictional force. And then our track angle, given that we are going to use an incline, we are going to use the same track angle theta, so that we do not have many independent variables and dependent variables. We only want to have one independent variable, which is the net force, and one dependent variable, which is the what? The acceleration. So now, since we do not have a physical setup where we can actually come and witness this experiment in a physical setup, I'm going to adopt a question that is usually asked in your exams that actually gives a picture of this experiment. That question is what we are going to use as our investigative setup. So that question is going to give us a setup, and then from that setup we are going to draw some questions from that setup and be able to use logic, be able to apply an experimental investigation in answering questions to do with the experimental setup, so that whenever we see that question, we would know what is it that is expected of us, and how do we answer certain questions, and how do we interpret certain experimental setups. So pardon me, I'm just going to use this question to drive through our experiment, instead of us physically doing this experiment and observing what happens and what becomes the relationship between force and acceleration. We are simply going to use an experimental question that has been determined already, so that we can be able to deduct and derive the relationship between force and the acceleration. After we have said that, let's look into this question. So I've adopted this question from a past exam question. So allow me to use this question as our practice experimental question setup. So the question was saying, grade 11 are asked to investigate the relationship between the net force and acceleration by pulling a trolley across a surface which is slightly inclined to compensate for friction. The trolley is connected to different masses by a string of negligible mass. The string passes over a frictionless pulley. Refer to the diagram below. So everything has been given within this diagram. This is our experimental setup. So in your classes, you might be having this physically, where you would have your trolley. You would also have an incline. Maybe you would use a table, and then you would also have a pulley within that table, and then you would have slotted masses. And then you would have inextensive strings as well. You would be able to use some blocks to have your constant track incline, where now you would use this trolley as well as these masses to derive and deduct the relationship between your net force against your acceleration. Where now what is going to happen is, since these masses would be constant, we would actually get to use this track incline to change our frictional force, so that the net force becomes the one that is changing due to the change in in our frictional forces, as well as our parallel gravitational forces. So as our net force would change, we would like to know what becomes our acceleration. So you would be having a ticker tape attached to the trolley that passes through a ticker time. So as it passes through the ticker time, you would see that this trolley would begin to move. As it moves, we would actually get to start recording the time it takes to move from one point to another. So that would determine either our speed is changing or remaining the same. Either our speed is increasing or decreasing. Then it will determine if the increase in net force is directly proportional to the increase in the acceleration, or else it's inversely proportional. That is how we would determine that. So the acceleration of the trolley is determined by analyzing the ticker tape. The results of the net force produced by the different masses as well will also be recorded. So after the experiment was done, there were some results that these grade 11 learners actually found. So those results are here. So these are the results that were given to say this is the net force that was determined, and this was the acceleration that was also determined given the net force that was being applied. So after that experiment was determined, after they done that experiment, they determined different variables, given that our net force was our independent variable and our acceleration being our dependent variable, we were now asked the following questions. We now need to be able to deduct certain conclusion from this experiment. Like, for example, the first question was saying, write down an investigative question for this experiment. What would you state as an investigative question? What can be the question, or else what can be an objective that you would need to actually determine at the end of the day using this experiment? So you would see that the aim of this investigation, as we have said before, now becomes to say, the aim of the experiment, as we have said, it is to investigate the Newton's second law. How to investigate the Newton's second law? This is through determining the relationship between the net force and the acceleration while keeping the mass constant. So that is what you would have came here and said, where they said determine or write down the investigative question for this experiment. You would come and say, what is the relationship between the net force applied, or else the net force, and the acceleration of the object? So pardon me there. Let me just try to reduce the font of our ink. Let me just try to reduce the font of our ink. So the investigative question would be to say, what is the relationship? We want to determine the relationship between the net force and the acceleration of the object. And the acceleration of the object. So that becomes our investigative question. That becomes our investigative question. That is our main objective of this experiment. What we want to determine is the relationship between the net force and the acceleration of the object. So as an investigative question, it would be to say, what exactly is the relationship between the net force and the acceleration of the object? After that, now the questions would come to say, identify the independent variable from the experiment that was carried out by the learners and from the results that were recorded by the learners. What would you identify being the independent variable? So as we have already stated, we said the independent variable is the what? Is the net force. The independent variable is the net force. And then the dependent variable is our acceleration. Because we want to vary the net force to get to see how our acceleration would vary as we vary our what? Our net force. And then thereafter, with these results and the experiment that has been carried out, they are now saying, use the graph paper on the answer sheet and draw a graph of the acceleration versus the net force. Now they want you to use these results to simply draw a graph, of the acceleration versus the what? The net force. So drawing a graph, you would simply come and draw your y-axis as well as your x-axis. So they've already told us that we need to draw the acceleration against the what? Against the net force. So if I were you, I would just come and determine my scale. After determining my scale, I will simply then go and plot my graph. So for example here, I can simply say, let what? Let 0.3 newtons be represented by, let it be represented by maybe 1 centimeter. So that after every 1 centimeter, I've got 0.3 centimeters. So it will be 0.3, 0.6, 0.9, and 1.2, and lastly 1.5. And then I would also come to my acceleration, and then I would see that I've got 0.36, 0.073, and ending at 0.15. I can simply use what? I can simply use maybe, let's say I would also use 0.3 meters per square second to represent what? To represent, I would simply use 1 centimeter to represent 0.3 meters per square second. So also this side, I'll say 0.3 meters per square second, 0.6, 0.9, 1.2, and then later go to 1.5. So that would be, or that would have been my scale. So I would have just came and neatly written here that I would have came and said scale, to say this is my scale. And then I would say on the y-axis, which is where I've got my acceleration, I have got 1 centimeter representing 0.3 meters per square second. We did this when we were doing vectors in what? In 2 dimensions. We need to first determine our scale and then later start plotting our graphs. Now, after that, I would also come and say on my x-axis, which is now my which is now my net force. Let 1 centimeter also represent 0.3 Newton. So that when I come and plot, I've already determined how my scale is going to be. Thereafter, I would come and start plotting my values. So 0.3 newtons here, I've got 0.3 newtons here, and then, so this would be this constant straight line of a 0.3 newton. And then I would go to 0.36. So maybe somewhere here, this is where I would be having my 0.36. So this becomes my constant 0.36 newton. So that where these two intersect, this becomes my first point. Where these two intersect, that becomes my first point. Where those two intersect, that becomes my first point. After that, I would also go to uh, 0.6. This is my 0.6 newtons. So I would simply draw a faint constant 0.6 newton line. And then I would go to, it corresponds to 0.73 meters per square second. So maybe 0.73 would be somewhere here. So that where these two intersect would be my second point. After that, I would go to 0.9. This is my constant 0.9 line. So at some point in time, using your graph grid lines, you would simply know that my 0.9 straight line constant line would be this. And then if I now go to 1.09, my 1.09 at some point in time would be, this is my line. So that where these two intersect, this is where I've got my what? My plot. After that, I would go to 1.2. This becomes 1.2. This is the constant straight line, 1.2 Newton line, and then I would go to 1.45. So at some point in time, 1.45 constant straight line would be this, so that I would be having my plot there. So after that, I would simply now ground my graph from 0.00 and then to my first plot as I go, as I go, as I go. So you would see that my graph would simply be a constant straight line graph. Sorry, it would just be a straight line graph, which represents a directly proportional relationship where I'm saying acceleration is directly proportional to my what? To my net force. So that was the graph that you were just supposed to draw there. That was the graph that you were just supposed to draw. You were just supposed to plot this against that. That is how you use the results from your investigation to what? To plot graphs. That is how you interpret investigative results, or else that is how you interpret your experimental results. Once you have done that, the next thing is just to actually guess to what? To follow through. So I would simply come here and then follow through the coming what? The next questions. Because I've already determined everything using my graph. So maybe I would want you to see the graph that was drawn uh, from from the given answer script that we had, which is our memorandum. So this is exactly that what they were expecting you to do with the graph that they had given you. So you can see that it is simply the same thing. A constant what? It is simply a straight line graph that is having your acceleration and your net force. So that is exactly what you are supposed to do there. So given that experiment, that is how you interpret it, and that is how you use those results to actually answer the given questions. Now let's answer the following question, which says calculate the gradient of the graph. Now the gradient of the graph, given this graph, the gradient of the graph, we know that gradient is given by what? change in y over change in x. I can take my y point at point 2 minus my y point at point 1 over my x point at point 2 minus x point at point 1, where I would simply choose this to be my point 2 and that to be my point 1, so that I've got y2, and then I would simply have, so here I would be having, I would simply have my x2, and then here I would be having my x1 and my y1. Or else, since here I don't have the value, I can simply come and use given values from that graph to say, I can use two given plots to say, okay, fine, let me use 1.2. Let me use 1.2. 1.2 was given to be, I'm sure this graph at some point in time, their graph at some point in time, it's inverted. They were supposed to have 1.45 against 1.2, but here they're having 1.2 against 1.45. Oh, yes. So this is where I've got my acceleration, and this is where I've got my force. But here my acceleration was supposed to be 1.45 meters per square second against 1.2 here. So this graph from it's just that I didn't take time to look at this graph. I'm seeing it now that they incorrectly plotted the graph. So this graph was incorrectly plotted. They were supposed to have it the other way. So we can just get to go back. We can just get to go back to our graph that we had drawn. We can just get to go back to the graph that we had drawn already. So this is the graph that we had where we were having 1.45. This is where you would have 1.45. And this is where you would have 1.2. So please, guys, let us not make the same mistake that they made on the memorandum. So this should have been the correct graph. So now, using this correct graph to actually determine the gradient, what you would have done, you would have said gradient given, maybe let's say by the letter m, would have been equal to, letter m is just representing gradient, or else let me say gradient, because if I say letter m, someone would think I'm now representing mass by that. Gradient would be equal to, let's say my point, I will take this point, which is given by that. That is to say, the y value here, the y value is 1.45. It will be 1.45 minus the y value on this plot. I'll take this value, which is 0.3. The y value there is 0.3. Divided by, I would come and take the x value here, it's 1.2, minus my x value here, it's also 0.3. So my gradient would simply have become 1.45 minus 0.3 divided by 1.2 minus 0.3. Given that my gradient was just supposed to be equal to, if I say 1.45 minus 0.3 divided by, so so let's punch in our calculators so that we get to cross check the answers that I'm going to get here, where we are saying 1.45 minus 0.3 divided by 1.2 minus 0.3. I'm getting a value of 1.27. This is the value that I'm getting, 1.277. So I'll round it off to 1.287. Or else let me say 1.278. It will be 1.278 in 3 decimal places. That would have been my gradient. My gradient would be 1.278 by using my graph. By using my graph. So by simply using my graph, I would have used that. Now, let's go to the following question. The following question is now saying, use the gradient of the graph calculated in question 3.4, which is this question, to actually determine the mass of the trolley. Now, this is where now we now take Newton's second law and apply it in this experiment. So here we have seen that acceleration is directly proportional to the what? To the force applied. And this is given by a law that we term Newton's second law, which says F net is equals to mass times acceleration. So from this relationship and from the gradient that we have just come out to get, which is to say the gradient being 1.278, where you would be having your acceleration against your F net, and you would get a gradient here where I would say the gradient, let me represent my gradient by the letter G, would be equal to what? To acceleration over net force. So you would see that my gradient here, my gradient is simply equal to acceleration all over my net force. If that is the case, from the relationship of net force is equals to mass times acceleration, how do I find my what? My mass. How do I find my mass from that relationship? From Newton's second law, you would find out that if I want to find my mass, I have to make it the subject of the formula. So it becomes mass is equals to net force divided by acceleration. If that is the case, you can see that now mass will now be simply equal to what? To the inverse of my gradient. It is simply equal to the inverse of my gradient, where it becomes 1 over acceleration over F net, because this will simply go to become F net over acceleration. Therefore, if I'm using that relationship now to determine the mass of the trolley, I will just need to invert that gradient that I have. So now the mass would be equal to 1 over 1.278. That would be the mass there. If that is the case, now let's find out what becomes our mass. 1 divided by 1.278. 1 divided by 1.278, it becomes 0.78. It becomes 0.782 kgs. That becomes our mass. So from the diagram, or else from the graph, let's say from the graph of acceleration against force, from this graph that we have determined the year, where we said it's acceleration against our net force, we now understand that the relationship is given by that graph. So the gradient here, the gradient that we get here is equal to 1 over mass. So that when you now want to find mass, this is also equal to 1 over gradient. You now need to know this. You now need to know this. That from this relationship, according to Newton's second law, you would know that since acceleration is directly proportional to net force, and this is the graph of acceleration against net force, for me to find the mass, I will now get to invert the gradient that I find, or else the gradient would now become 1 over mass. We now need to know this relationship. After we've said that, let's also go on to another example that has to do with the same experiment, and see how we can be able to use our deductive minds to actually get to determine the relationship of the what? Of the net force against the what? The acceleration, or else to verify the Newton second law using the same experiment. Now, I also brought another question from another question paper, which is saying the graph below represents the data obtained in an experiment that aims to verify Newton's second law of motion. So, as a recap, we are dwelling much on the Newton's second law because in your grade 11 they are going to examine you on the experiment or else on the investigation that you are going to do at your school, that is to investigate or determine how the net force varies or else how the net force relates to the what, to the mass or else to the acceleration of the what, of the object, which is just investigating the what, the Newton's second law. So given that, this is the reason why I've brought these two questions so that we can be able to relate, so I want us to also use this following question in determining what is to fall. So this is the graph that they are saying. They are saying the graph below uh, represents the data obtained in an experiment that aims to verify Newton's second law of motion. And this is the graph. This is the graph where we have got y against f net. We do not know what is y and what is z. Now, given that, let's hear what the following question actually means, or what the following question is saying. The following questions are saying now, state the Newton's second law of motion in words. What does the Newton's second law states in words? We know that if a net resultant force is applied to an object, the object will accelerate, with an acceleration that is in the, or else that is directly proportional. Let's say that is directly proportional that is directly proportional to the net force. That is directly proportional to the net force applied. But inversely proportional to the mass of the object. In the same direction. So the acceleration will be in the same direction. The acceleration will be in the same direction with applied force. So you would see that Newton's second law, it simply states that if a net resultant force is applied to an object, the object will accelerate. Let's say we have got an object and we have got a net resultant force applied to this object A. This object A will start to accelerate, and the acceleration will be directly proportional. The acceleration will be directly proportional to the net force applied, but the acceleration would be inversely proportional to the mass of the object, and the acceleration would be in the same direction as the net force applied. That is what Newton's second law states in words. So that is what you need to know, and that is what you need to understand. So you need to read and understand and actually master this definition by head, because they will ask you to state all the Newton's laws by head. They might start by Newton's first law, Newton's second law, Newton's third law. And we are also going to do Newton's universal gravitation law. After that, they're now saying, write down the quantity represented by y with the correct units. What is the quantity represented by y? What might be the quantity represented by y? Where we draw y against f net, and we have got a straight line graph which represents directly proportional. This simply means that it's what? It's acceleration. Acceleration. Represented by the letter A, with the SI units given by meters per square second, because acceleration is the only variable that is directly proportional to the net force. So that's the only variable where you would draw your graph against the net force and have a straight line graph. So here you would have just came and said what? Acceleration. You would have said what? Acceleration. So here they said, write down the quantity represented by the letter what? By the letter y, it's acceleration. The correct units, meters per square second. Use the graph to calculate the mass of the trolley. Now, we now know that the mass of the trolley from the acceleration against force graph, the mass is given by the inverse of the gradient. That is what we just said from the previous question. So our mass would be given by 1 over the gradient of the what? Of the graph. So what we simply need to do is to determine the gradient at first. What we simply need to do is to determine the gradient at first. So what we can do is we simply need to determine the gradient. So what is our gradient? You would simply say gradient is equal to y2 minus y1 over x2 minus x1. Now, what is my y value? So I'll take this plot and take maybe that plot. So I'll take this one. I have y2, and then I have x2, I have y1, I have x1. So y2 here is what? It's 1.5 minus y1, it's 0.5. I have got 1.5 and 0.5 divided by, what is my x2? My x2 here, it's 4.5. I would say 4.5 minus 1.5 minus 1.5. This would give me what? This will give me 1 divided by what? Divided by 3, which is simply equal to what? 0. What? 1 divided by 3. 1 divided by 3. 0.33. 0.33333. 0.333333. So that is the gradient. After I found my gradient, I know that what I'm looking for is the mass. What I'm looking for is the mass, and I know that mass is 1 over the what? The gradient. So what I can simply do, it's 1 over 3, which is simply equal to what? To 3 kgs. Or else, this is simply equal to 1 over 0.33333. You would see that this is equal to what? 3 kgs. Let's use our calculators to actually verify those answers. So that is how you would have determined your answer. So we have agreed that the inverse of the gradient of the graph of mass, of the graph of what? Acceleration against force, gives you your mass. How you determine the mass from the graph of acceleration versus the net force is through the inverse of the gradient, because you have got a straight line graph there. So from there, we have determined this to be equal to 3 kgs, because your mass is measured in kgs. Determine the value of z. Now we now need to determine the value of Z. Where is Z? There is Z. We now need to determine the value of what? The value of Z. Since we now know the gradient, we can use the gradient. We can use the gradient to say gradient is equals to y2 minus y1 over x2 minus x1. And we said the gradient is 1 over 3. Y2, that's Z, minus y1, I can choose to take this one, 0.5, 0.5, divided by x2, it's 8, minus x1, it's 1.5. So if that is the case, or maybe let me use whole number values. I would use this as 2 and this as 1. So that I can say y2 it's z minus y1 it's 1. Divided by x2 it's 8, x1 it's 3. I just wanted to use whole number values there. Just pardon me. Now, after I've done that, z1 minus 1 is divided by 8 minus 3, it becomes 5. And this side I've got 1 over 3. I can cross multiply by 5. I can cross multiply by 5, cross multiply by 5, so that I can remove that. This side I'm left with z minus 1 being equal to what? 5 times 1 over 3. 5 over 3. Now I would transpose 1 that side, so that I would be left with what? 5 over 3 plus 1 being equal to z. And what becomes our z? If we say 5 divided by 3, 5 divided by 3 plus 1, that becomes 2.66. That becomes 2.67. Let's just say 2.67. So the value of z here would have been what? 2.67. That is how you would have determined the value of z. After we are done with that, we now know and understand how to investigate the Newton's law and how to actually interpret data from that experiment, and how to determine the relationship between your net force and acceleration, your mass, and the relationship between the graph of acceleration and net force, how to determine mass from that graph, how and yes, how to determine the values and plot the graph of acceleration and what? Net force. After we now know that, all we are now left with is applying Newton's second law in working out problems to do with many forces or different types of forces. We now know this law, that net force is equals to mass times acceleration. We now need to apply this law in determining the net resultant force, given that we have got what? More than one force. Given that we have got more than one force acting on a board. More than one force acting on a board. That is what we now want to go and do. So in our next video, we are going to apply this force in determining the net resultant force when we are given more than one force acting on a board. So let's meet in our next video class for grade 11s to come. This is your guy from Met Zone African Motive. Thank you.